New research suggests the interstellar object 3I Atlas is unusually massive and far larger than expected. A team from Harvard estimates the comet's core weighs over 33 billion tons, with a diameter of roughly 5 kilometers, not counting the surrounding coma. That appears to be about 3 to 5 orders of magnitude more massive than earlier interstellar visitors. This finding has profound implications for our understanding of interstellar objects and raises fundamental questions about what we should expect to encounter from beyond our solar system. Figuring out how big a comet really is can be difficult. The challenge lies in telling the nucleus apart from the hazy coma around it. As a comet draws closer to the Sun, its frozen ices turn directly into gas, dragging streams of dust out into space with them, which forms their distinctive trail or coma. This can make the comet appear far larger and brighter than the solid body itself. The visual spectacle we associate with comets, the glowing head and sweeping tail, can be misleading when trying to determine the actual size of the rocky or icy nucleus at the heart of these celestial wanderers. The difficulty in measuring cometary nuclei has challenged astronomers for generations. Traditional methods rely on observing how bright a comet appears and making assumptions about its reflectivity, but these approaches carry significant uncertainties. The coma can extend for hundreds of thousands or even millions of kilometers, while the nucleus itself might be just a few kilometers across. Separating signal from noise requires careful analysis and sophisticated techniques. A team from Harvard, led by Richard Kluder, Avi Loeb, and Peter Vest, developed a different approach. They analysed observations of 3I Atlas collected between May 15th and September 23rd from 227 different observatories worldwide via the Minor Planet Center. This massive data collection effort represents one of the most comprehensive observational campaigns ever conducted on an interstellar object. The global network of observers provided continuous coverage as the comet moved across the sky. The researchers compared the actual trajectory to the path we would expect if only gravity acted. In principle, if a comet was simply falling through space under the influence of the Sun's gravity, its path would follow a precise mathematical curve. Any deviation from that ideal trajectory indicates that other forces are at work. What they found was a tiny but noticeable push, less than 15 meters per day squared. While this might sound small, it's large enough to measure with precision and significant enough to reveal important information about the comet's properties. Comets with active outgassing usually get a slight push from the jets of escaping gas. As sunlight warms the nucleus, volatile materials sublimate, turning from solid ice directly into gas. This gas doesn't escape uniformly in all directions. Instead, it erupts in jets from active regions on the surface. These jets act like tiny rocket engines, giving the comet a small but measurable acceleration. By observing how much a comet deviates from a purely gravitational orbit, astronomers can learn about the strength of its outgassing. In 3I Atlas's case, the measured non-gravitational acceleration is surprisingly low relative to the observed outgassing. The comet is clearly active, with visible jets and a developing coma, yet it's barely being pushed off course. That suggests the nucleus is heavy enough to resist being pushed around much by those jets. It's like the difference between trying to move a basketball with a garden hose versus trying to move a boulder. The same force produces dramatically different results depending on the mass of the object. From this analysis, the researchers estimate the comet's core weighs over 33 billion tons with a diameter of roughly 5 kilometers. To put this in perspective, 33 billion tons is approximately 33 trillion kilograms. This makes 3I Atlas substantially more massive than typical comets we've studied in our own solar system. The 5-kilometer diameter places it in the size range of some of the larger cometary nuclei we know, but its density appears to be much higher than expected. The implications become even more striking when we compare 3I Atlas to earlier interstellar visitors. The first confirmed interstellar object, ʻOumuamua, passed through our solar system in 2017. It measured only a few hundred meters across and had an estimated mass many orders of magnitude smaller than 3I Atlas. The second interstellar visitor, 2I Borisov, was discovered in 2019 and appeared to be a fairly typical comet, perhaps a kilometer or so in diameter. 3I Atlas appears to be about 3 to 5 orders of magnitude, more massive than these earlier interstellar visitors. That means it could be anywhere from 1,000 to 100,000 times more massive. Loeb has argued that given what we expect about the available population and heavy element abundance in interstellar space, we should by now have seen far more interstellar objects of more modest sizes before stumbling into one so massive. The logic is straightforward. Smaller objects should be far more common than large ones, just as pebbles outnumber boulders on Earth. If interstellar space follows similar statistical distributions, we should detect dozens or hundreds of small interstellar objects for every massive one. Yet we haven't. That marks 3I Atlas as a significant outlier. This statistical anomaly raises profound questions. Are our detection methods somehow biased toward finding larger objects? Is the population of interstellar objects fundamentally different from what we expected? Or is there something unusual about 3I Atlas specifically? The answers to these questions will shape our understanding of material exchange between star systems and the processes that eject objects into interstellar space. Loeb even entertains a speculative alternative hypothesis that the object could be of technological origin, citing the unexpectedly large mass, the alignment of its trajectory, and some purported detection of nickel without iron as provocative hints. This hypothesis is not confirmed. The idea of a technological origin for interstellar objects gained attention after ʻOumuamua's unusual acceleration and elongated shape sparked debate. While most scientists favour natural explanations, Loeb has consistently argued for keeping all possibilities on the table until we have definitive evidence. NASA scientists, however, urge caution. The prevailing view remains that it is most likely a natural object. From images, we also saw that this object is active, which means that around the nucleus there is some coma, which is an indication that this object is in fact a comet. The presence of outgassing and a coma are hallmarks of cometary behaviour. Technological artifacts would not be expected to exhibit these characteristics. The scientific consensus leans heavily toward a natural, if unusual, comet. Meanwhile, some scientists aren't asking what 3I Atlas is, but what its purpose might be. This shift in perspective opens up fascinating possibilities about the role interstellar objects play in the broader cosmic ecosystem. Astrophysicist Suzanne Felsner's idea is simple but striking. 3I, Atlas, may be a planet-making seed, but how can a wandering rock from another star system spark the birth of an entire planet? The answer lies in the complex physics of planetary formation. We enter a young solar system where a new star sits at the centre of a great dusty ring. Here, tiny grains of rock swirl like smoke, clumping together into pebbles. With time, they snowball into boulders and then into planetesimals, the raw ingredients of planets. This process, known as accretion, is how planets are thought to form throughout the universe. Given enough time, these planetesimals grow massive enough to gather even more material through gravitational attraction. It sounds straightforward, but as we'll see, there's a serious problem with this picture. Disks only last a few million years before the gas is blown away. The young star's radiation and stellar wind gradually dissipate the gas in the protoplanetary disk. That window seems too short to explain how massive planets like Jupiter and Saturn were able to form. Theoretical calculations suggest that building a Jupiter-sized planet from dust grains alone requires more time than the disk typically survives. This timing problem has puzzled planetary scientists for decades. Now imagine a different scenario. Into this disk falls an interstellar object, a body already big enough to serve as a ready-made core. Instead of starting from dust grains, the disk suddenly has a solid seed that can immediately start pulling in surrounding gas and material. In this way, an alien traveller could speed up the birth of a new planet. The interstellar object bypasses the slow initial stages of accretion and provides an instant gravitational anchor around which a planet can rapidly assemble. Felsner's simulations support this idea. She found that massive stars are better at capturing interstellar objects than smaller ones. More massive stars have larger gravitational influence, and their protoplanetary disks extend over greater distances, providing a bigger target for passing interstellar objects. And sure enough, gas giants are more common around bigger stars. Observational surveys have confirmed this correlation. The match between theory and observation is striking. If this is true, then interstellar objects like ʻOumuamua, Borisov, and Atlas aren't just drifters. They may be the sparks that ignite planetary systems. Some might have seeded gas giants in faraway systems. Others may even have played a role in our own solar system's early history. Perhaps Jupiter or Saturn began their existence as captured interstellar objects that then accumulated the gas and material we see today. It's a bold idea and still unproven. The hypothesis remains speculative, but it offers an elegant solution to the timing problem in planet formation. Interstellar objects are notoriously difficult to study. They appear suddenly, move quickly, and vanish into the dark. By the time we detect them, they're often already leaving the inner solar system. ʻOumuamua was discovered only after it had already passed closest approach to the Sun. Borisov gave us more warning, but even then the observing window was limited. But this time we're ahead of the curve as we have detected it well in advance, and our technology may finally let us uncover its true nature rather than just guessing after it's gone. The European Space Agency is preparing Mars Express and the ExoMars Trace Gas Orbiter to observe 3I Atlas as it passes near Mars in October 2025. These spacecraft aim to capture images and data we've never had before of an interstellar object. Mars Express has been orbiting the red planet since 2003, and its high-resolution cameras could provide unprecedented views of the comet. The ExoMars Trace Gas Orbiter, which arrived at Mars in 2016, carries instruments designed to study atmospheric composition. These same instruments could analyze gases in the comet's coma. Whether from orbit around Mars or from telescopes back on Earth, the coming months are set to provide a rare opportunity to track an interstellar object in detail. Ground-based observatories around the world will coordinate their efforts to maintain continuous coverage. Space telescopes operating at different wavelengths will contribute complementary data. This multi-platform approach maximizes our chances of capturing every detail of the comet's behavior as it traverses the inner solar system. Astronomers have pinned several key milestones to their calendars, landmarks to watch as this visitor races through our cosmic neighborhood. October 3, 2025, Mars flyby. Just after sunrise over Valles Marineris, the comet will plunge past the red planet a mere 18 million miles away. Valles Marineris is a vast canyon system on Mars, and the timing of the flyby will place it in view from this dramatic landscape. From orbit, MAVEN and Tianwen-1 will see its dusty coma start to glow faintly pink in the Martian dawn. MAVEN, NASA's Mars Atmosphere and Volatile Evolution mission, and Tianwen-1, China's Mars orbiter, will both be positioned to observe the event. October 29, 2025, perihelion. 4 weeks later, 3I Atlas will sling behind the Sun, skimming to 1.36 astronomical units, which is about 130 million miles from the photosphere. Perihelion marks the point of closest approach to the Sun, where the comet experiences maximum heating. Here, its speed peaks near 152,000 miles per hour. The comet will be moving at a significant fraction of the escape velocity from the solar system. At this point, the comet is lost to Earth-based telescopes, hidden by solar glare. The Sun's overwhelming brightness makes it impossible to observe objects that pass too close from our vantage point. But spacecraft on Mars and at L1 will keep a watch as jets of vapour erupt from the freshly warmed crust. The L1 Lagrange point, located between Earth and the Sun, provides a stable position for solar observatories. Spacecraft stationed there can observe regions of the sky that are blocked by solar glare as seen from Earth. These platforms will monitor the comet continuously during its closest approach, documenting any changes in activity level or outgassing patterns. December 19, 2025, Earth distance check. With its tail now fully unfurled, 3I Atlas will pass Earth at a comfortable 170 million miles. By this time, the comet will have rounded the Sun and will be heading back out toward the outer solar system. Too far for a naked eye view, but close enough for the James Webb Space Telescope and Vera Rubin Observatory to rake its coma for isotopic clues. The James Webb Space Telescope can analyze the chemical composition of the coma in exquisite detail. The Vera Rubin Observatory, with its wide field of view and sensitive detectors, can track subtle changes in the comet's appearance over time. Isotopic ratios provide a chemical fingerprint of where an object formed. Different stellar environments produce different ratios of isotopes like deuterium to hydrogen or nitrogen-15 to nitrogen-14. By measuring these ratios in 3I Atlas, astronomers can potentially identify which type of star system it came from and under what conditions it formed billions of years ago. March 16, 2026, Jupiter Pass. Finally, the visitor will fly past Jupiter, 33 million miles above the gas giant's clouds. This encounter will provide a final opportunity to observe the comet before it exits the solar system entirely. If NASA approves a late course tweak, the Juno spacecraft could swing out to sample the comet's dust stream, providing our sole up-close look at material that formed beyond the Sun. Juno is currently in orbit, around Jupiter, studying the planet's atmosphere, magnetic field, and interior structure. Diverting it to encounter 3I Atlas would be a challenging maneuver, but the scientific payoff could be enormous. After that, 3I Atlas will curve back into interstellar space, leaving behind terabytes of data and a lot of questions. The data collected during these observations will keep scientists busy for years, analysing every spectrum, every image, every measurement to extract the maximum possible information about this mysterious visitor. The questions raised by its unusual mass, its trajectory, and its place in the broader population of interstellar objects will drive future research and shape the next generation of detection programs designed to find and study these rare travellers from beyond our solar system.